Does free will truly exist? Or are all our decisions part of a predetermined script? Science suggests that quantum experiments can be used to seek an answer to this question, which has existed since the dawn of humanity. Testing one of philosophy's most complex problems, free will, with quantum physics. The moment we hear this proposition, a single question comes to mind, especially for those of us who are merely science enthusiasts. Where's the intersection of free will and quantum physics? Whatever you do related to quantum physics, you proceed from a very fundamental assumption: measurement independence. This means that the choice of which measurement the experimenter, say to imaginary scientists like Alice and Bob, will make should not depend on a hidden state within the system. In other words, even if there are hidden variables in the universe, they shouldn't be interfering with which experiment or measurement we decide to perform. But what if that's not the case? What if the experiment we choose to do, or the measurement we decide on, is somehow connected to those hidden variables? That's when things get complicated. This means that if there's a limit to what you can achieve, no matter what you measure or choose, it would be very difficult to tell someone who says, even if you have free will, it is only a limited free will, that they are wrong. This concept is already defined in the scientific community as the free will loophole. Because if this situation exists, it could mean that our free will is at least partial or only valid within certain limits. This is precisely where free will and quantum physics intersect. If you ask how this can be tested, the first answer scientists give is Bell's inequality. The scientists who conducted this experiment have already received the Nobel Prize. If hidden variables exist in the universe, the correlation between the measurement values of two quantum particles cannot exceed a certain limit, regardless of whether these particles are entangled. The violation of Bell's inequality, named after John Stuart Bell, is the surpassing of this limit we just mentioned. In his 1964 paper, John Stuart Bell drew the boundaries of determinism in the language of mathematics. That's why those who experimentally demonstrated this were deemed worthy of the Nobel Prize. Although explaining Bell's inequality is beyond our scope, let's give it a try. Bell's inequality proposes a thought experiment, which was initially presented mathematically and later turned into a real experiment. Alice and Bob are two observers located very far from each other. They each measure a particle that reaches them at the same time. However, they choose their measurement directions randomly each time. Let's say they are both going to measure a spin value. In quantum mechanics, the spin of a particle can be thought of like the direction of rotation of a top, but we can measure this rotation not just in one direction, but in many different directions. For example, let's take an electron. Its spin can be measured not only up-down, but also right-left or forward-backward or combinations thereof. So, the spin value is not a one-dimensional measurement. It has multiple measurement directions that you can choose. According to this thought experiment, Alice has two choices for her measurement: to measure the particle from direction A or direction A. Bob also has two choices. He can measure the particle from direction B or direction B. Each particle carries a predetermined, implicit answer for each of these four measurement directions. When the particles are measured from one of the directions A, B, or B, they yield a result of either +1 or 1. It's as if the particle carries a hidden instruction sheet. In essence, it contains a deterministic set of rules. In this thought experiment, the hidden rule set is very simple. If Alice chooses direction A, she will get a result of +1. If she chooses A1, she will get -1. If Bob chooses direction B, he will encounter a value of -1. If he chooses B1, it will be +1. In fact, here Bell has defined a deterministic function dependent on the chosen direction. These instructions are fixed before the particle is even sent or measured and do not change in any way during the measurement. Alice and Bob freely decide when and which direction to choose, but they are unaware of the function they are a part of. When they make a measurement, they only receive the result that the particle has stored for that specific direction. Bell's inequality then examines the correlations of the measurements made by Alice and Bob. Alice made a decision and a measurement. Simultaneously, Bob made a decision and a measurement, and these results were recorded. And this process was repeated thousands of times. As a result of the records of thousands of measurements, the maximum possible sum of the correlations that can mathematically emerge between Alice's and Bob's measurement values is calculated. According to these calculations, if the universe operates entirely according to deterministic rules, no matter which measurement directions Alice and Bob choose, the sum of the resulting correlations cannot exceed the value of 2. This limit was first established by John Bell. For some, this value represents the point where determinism ends and quantum mechanics, and perhaps even free will, begins. However, in experiments conducted using quantum entanglement, it has been observed that the correlations between measurement results exceed this limit, reaching up to a maximum value of 2.828. Thus, if quantum entanglement is involved, it is possible to surpass the limits predicted by deterministic rule sets in terms of correlation sums. While some see this result as direct proof of the existence of free will, the fact that the measured correlations still have a specific upper limit, approximately 2.828, also strengthens the hand of those who argue that free will is not absolute, but limited. However, the number of people who claim that this experiment alone definitively proves the existence of free will is quite small. This is because reaching such a significant conclusion based on a random decisions of only 2 people, thereby completely ignoring the lack of free will, is considered an interpretation that requires a cautious scientific approach. Therefore, it is quite meaningful to look at the results of an experiment involving many more people. This idea is not illogical. With this approach, a very interesting experiment called the Big Bell Test was conducted in 2016. In this experiment, more than 100,000 volunteers from around the world came together to test Bell's inequality. The participants generated over 97 million random bits by playing a game accessible via the internet. These bits were transmitted in real time to quantum experiment setups in various laboratories and determined the measurement settings for entangled particles. The most remarkable aspect of the experiment was that the measurement settings were determined entirely by humans, consciously yet randomly. Volunteers tried to generate 0 and 1 values as randomly as possible through a video game. The average of this data was then used to decide whether to measure in direction A or A in each measurement. Since we will cover this experiment in detail in a separate video, we will leave the details of the records for later. However, it should be noted that as a result of the completely random decisions made by 100,000 people, the correlation between the measurements in the test on 2 quantum entangled particles was observed to exceed the value of 2. In other words, in these measurements using millions of individually randomly chosen bits, Bell's inequality was again violated. This showed that even a massive decision-making mechanism of 100,000 people can produce a result that is impossible in classical physics when quantum entanglement is present. In other words, even with such a large-scale human participation, quantum correlations can exceed the deterministic limits predicted by Bell. However, there have been those who argue that this situation also cannot completely overcome the problem of the limitation of free will. They argue that the fact that people's decisions are directly linked to the moment the experiment is conducted could cast a shadow on true randomness. Therefore, some researchers have suggested that if the randomness of the decisions were determined completely independently of the present moment, another step could be taken towards establishing the existence of free will. The experimental design proposed in a recently published paper based on this idea is quite remarkable. In this experimental proposal, the decisions are considered to have been made, in the literal sense of the word, billions of years ago. At the beginning of the experiment, Alice's and Bob's decisions are determined by 2 giant telescopes focusing on photons coming from stars that are 5 billion light-years away. Since it takes 5 billion years for the photons from these stars to reach Earth, the moment of their creation corresponds to 5 billion years ago in our timeline. Therefore, the measurement decision determined by these photons is considered to have been made at a time before the Earth had even formed. According to this setup, the telescopes capture these photons from the stars and transmit them to the measurement system that will decide in place of Alice and Bob. For example, if the photon captured by Alice's telescope is horizontally polarized, Alice measures in the spin x direction. If it is vertically polarized, she performs the measurement in the spin y direction. Bob similarly determines his measurement direction based on the polarization of the photons captured by his own telescope. If the results of the measurements made using this method again violate Bell's inequality, then the following conclusion can be drawn. Deterministic rule sets were not valid not only in the present time, but even 5 billion years ago. In other words, it would seem that even in those ancient eras of the universe, there was no predetermination. Of course, this experiment has not yet been conducted, but we will share it with you as soon as it is implemented and its results are published.